Types of molecular orbitals. Types of molecular orbitals. Okay. Molecular orbitals are three types. Molecular orbitals are three types. Okay. First is BMO. First is BMO, bonding molecular orbitals. BMO, bonding molecular orbitals. Okay. A bonding molecule is obtained by the combination of electron waves of the same sign by the addition overlap of atomic orbital. It has lower energy than the atomic orbitals from which it is formed. The electron density between the nucleus high. Okay, hence it is establishes the molecules. Second, non-bonding molecular orbitals. Non-bonding molecular orbital. Non-bonding molecular orbitals. Okay. Orbitals which are inside the inner shell of atoms which do not participate in the formation of molecules. Non-bonding electrons do not participate in the chemical bond formations. Hence, their presence do not affect the stability of the molecule. They remain unaffected, so their energy is also constant. Okay? Orbitals which are inside the orbitals which are inside the inner shell of atoms which do not participate in the formation of molecule. Okay. Non-bonding electrons do not participate. Non-bonding electrons do not participate in chemical bond formation. Hence, their presence do not affect the stability of molecule. They remain unaffected, so their energies also constant. Non-bonding molecular orbitals. Second, non-bonding molecular orbitals. Orbitals which are inside the inner shell of atoms which do not participate in the formation of molecule. Non-bonding electrons do not participate in chemical bond formation. Hence, their presence do not affect the stability of molecules. They remain unaffected, so their energy is also constant. Third point. Types of molecular orbitals mean third. Three types, there are third types. Antibonding molecular orbitals. Antibonding molecular molecular orbitals, antibonding molecular orbitals, ABMO, ABMO, okay, antibonding molecular orbitals, ABMO. Third is ABMO, antibonding molecular orbitals. It is formed by the combination of electron wave of opposite sign, hence it is formed by the subtraction overlap of atomic orbitals. It has higher energy than the atomic orbitals from which is formed. The electron density between the nuclei is very low. Hence repulsion occurs between the nuclei of atoms. So it de-establishes the molecules. The bonding molecular orbital has the bond forming tendency, while the antibonding molecular orbital has bond breaking tendency. Okay? It is formed by the combination. It is formed by the combination. It is formed by the combination of the electron wave of opposite sign hence it is formed by the subtraction overlap of atomic orbitals. It has higher energy than the atomic orbitals. From which it is formed. Okay? It is formed. The electron density between the nuclei is very low. Okay? Hence repulsion occurs between the nuclei of atoms. So it de-establishes the molecule. Okay? The bonding molecular orbitals. Has the bond forming tendency, while the antibonding molecular orbitals has bond breaking tendency. tendency. Okay. Antibonding molecular orbitals ABMO. It is formed by the combination of the electron wave of opposite sign. Hence, it is forming the subtraction overlap of atomic orbitals. It has a higher energy than the atomic orbitals from which it is formed. The electron density between the nuclei is very low. Hence, repulsion occurs between the nuclei of atoms, so it destabilizes the molecule. The bonding molecular orbital has the bond forming tendency, while the anti-bonding molecular orbital has bond breaking tendency. Okay. Next is the difference between bonding and anti-bonding molecular orbitals. Okay. 1 minute. Difference between bonding and anti-bonding molecular orbitals. Bonding molecular orbitals, this is BMO, bonding molecular orbitals, and this is ABMO, anti-bonding molecular orbitals, anti-bonding molecular orbitals. Okay. Then difference BMO, first point in BMO, it is formed by the addition overlap. It is formed by the addition overlap. It is formed by the addition overlap of atomic orbitals. Okay. Then psi BMO equal to psi A plus psi B, and it is formed by the subtraction. It is formed by the subtraction overlap of atomic orbitals. Okay. Then psi ABMO equal to psi A minus psi B. Second point. It has lower energy than the atomic orbitals. It has lower energy than the atomic orbitals from which it is formed. Okay. It has higher energy. Than the atomic orbitals. From which it is formed. Okay. Third point. Electron density. It has lower energy than the atomic orbitals from which it is formed, and it has a higher energy than the atomic orbitals from which it is formed. Okay. Third point. Okay. Third point. Electron density in between the nucleus. Electron density in between the nuclei of bonded atoms is high. Bonded atoms is high. Okay. Third point, so Electron density in between the nuclei of bonded atoms is low. Electron density in between the nuclei of bonded atoms is low. Okay. Fourth point. It establishes the molecule. It stabilizes the molecule. Okay, and it destabilizes the molecule. It destabilizes the molecule. Okay, the electron in the bonding molecular orbital in BMO. Fifth point. Okay, the electron in the BMO, the electrons in the bonding molecular orbitals, okay, tend to favor stable bond formation. Okay, and the electron in the antibonding, the electron in the antibonding molecular orbitals tend to oppose bond formation. Okay, bond formation. Okay, and next is energy level of different molecular orbitals. Okay, energy levels of different molecular orbitals. Okay, the molecular orbitals involved in the formation of simple molecular are given below. BMO, bonding molecular orbitals is that sigma 1s, sigma 2s, sigma 2px, pi 2py, and pi 2pz, and ABMO, anti-bonding molecular orbitals. Okay, sigma star 1s, sigma star 2s, and sigma star 2px, and pi star 2py, pi star 2pz. Okay, energy levels of various molecular orbitals in order of energy. Increasing energy are given. Sigma 1s is the less than sigma star 1s is the less than sigma 2s is the less than sigma star 2s is the less than sigma 2px is less than pi 2py equal to pi 2pz is less than pi star 2py is equal to pi star 2pz is less than sigma star 2px, sigma star 2px, okay, sigma star 2px. Sigma denotes the molecular orbital forming sigma bond, okay. Sigma denotes the molecular orbitals forming sigma bond, and pi denotes the molecular orbital forming pi bond, and star denotes ABMO, antibonding molecular orbitals. The energy of sigma 1s, is minimum, okay. The energy of sigma 1s is minimum energy of sigma star 2px, 2px, okay, sigma star 2px, okay, is maximum, okay. The energy of sigma 1s is minimum, energy of sigma star 2px is maximum, okay. And you can also show the below represent the energy level of molecular orbitals of 2p, orbitals of homodiatomic molecules like nitrogen, oxygen, fluorine, etc. While next figure represents the molecule like boron and carbon. You can show this is 2p and this is 2p, okay, and this is energy, and okay, this is 2py, this is 2py, and pi 2py, this is pi 2py, and this is pi 2pz, okay, pi 2pz, and this is BMO, bonding molecular orbitals, and this is pi star 2py, and this is pi star 2pz, okay. This is ABMO, anti-bonding molecular orbitals, because star is show the anti-bonding molecular orbitals, ABMO, and this is sigma 2px, and this is This is a sigma 2p X but star because this show the antibonding molecular orbitals. This is figure is for nitrogen, oxygen, fluorine, nitrogen, oxygen, fluorine, and next figure. This is 2p. This is 2p, and this is 2p. This is 2p, and this is 2p. And they show the you can also show these figures. This is pi 2py, pi 2py, and this is pi 2pz, pi 2pz, and this is pi star. That means antibonding molecular orbitals 2py, and this is pi star 2pz, pi star 2pz, and this is sigma 2p x, and above sigma star sigma star 2px. Okay, this is a figure of boron and carbon, boron and carbon, boron and carbon. Okay, okay, and next is a filling up of molecular orbitals, filling up of molecular orbitals, filling up of molecular orbitals. Okay, filling up of molecular orbitals, filling of molecular orbitals, filling up of molecular orbitals. The molecular orbitals are filled in the following order. The molecular orbital having lowest energy is filled up first, and sigma 1s is filled up first, while sigma star 2px in the last. Okay, first point. The molecular orbitals having lowest energy is filled up first. Lowest energy is filled up first. Hence sigma 1s is filled up first, while sigma star 2px in the last. Okay, second point. Each molecular orbital can hold only 2 electrons. Each molecular orbitals can hold only 2 electrons. Okay. Third point, as pi 2py and pi 2p z have same energy, have same energy, hence then field, hence then field, according to Hund, according to Hund's rule, okay. Then and pi star 2py and pi star 2pz also follow Hund's rule in filling of electrons, okay. Bond order. Next is bond order, okay. Bond order is the effective number of bonds between two atoms in a compound. Bond order is the effective number of bonds between two atoms in a compound. It is also described as the number of covalent bonds in a molecule. It is given the expression bond order equal to Nb minus Na upon 2, where Nb equal to number of electrons in bonding molecular orbitals, number of electrons in BMO, okay, number of electrons in bonding molecular orbitals, and Na equal to number of electrons in antibonding molecular orbitals, ABMO, okay. When the number of electrons in bonding and antibonding molecular orbital is equal, the bond order is 0. If Nb equal to Na, that means number of electron in BMO is equal to number of electron in ABMO, so bond order equal to 0. And such type of molecular orbital is called non-bonding molecular orbitals. And such types of molecular orbitals is called NBMO, non-bonding molecular orbitals. If there are 2 electrons in bonding and 2 electrons in antibonding molecular orbitals, the bond order is 0, is that no bond formation occurs, okay. The bond orders 1, 2 and 3 represent single, double and triple bonds, okay. It can be fractionalized also NO, BO equal to 2.5. It also indicates about the stability of bonds. It is obvious that higher the bond order, shorter is the bond length and so greater is the bond strength, okay. Stability of molecule on the basis of bond order, okay. Next is the stability of molecule on the basis of bond order, okay. Stability of molecule on basis of bond order, stability of molecules in the basis of bond order, okay. Stability of molecules on the basis of bond order, stability of molecule on the basis of bond order. First First one, if the value of bond order is positive, then the molecules will be stable. Okay? If the value, if the value of value of bond order is positive, then the molecule will be stable. Then the molecule will be stable. The molecule will be stable. Okay. Second point, if the value of bond order is negative, if the value of bond order is negative, if the value of bond order is negative or zero, it indicates that the molecule is unstable. Molecule is unstable. Okay? Molecule is unstable. Third point. The stability of molecule is determined with the help of bond dissociative energy. Okay? The stability of molecule is determined. The stability of molecule is determined with the help of bond. Dissociation energy. Dissociation energy. Okay? Dissociation energy. It is directly proportional to bond order. It is directly proportional to bond order. It is directly proportional to bond order. Okay? And nitrogen molecule with bond order 3 has higher dissociation energy, 225 kilocalorie per mole, than oxygen molecules with 118 kilocalorie per mole. Okay? With the bond order of equal to 2. Hence, molecule having greater number of bond order are more stable. Okay? Fourth point. Point 4. Bond orders, hence molecules having greater number of bond order, molecules having greater number of bond order, greater number of bond order. Okay? Greater number of bond order are more stable. Okay? Next, fourth point. 1 minute. Fourth point. Bond order is directly proportional to the bond strength. Bond order is directly proportional to the bond strength. Okay? Bond strength, but inversely proportional to, bond order is inversely proportional to bond order is inversely proportional to universally bond order is universally proportional to bond length. Bond length. Bond length. Okay. Thus, more will be bond order, shorter is bond length. Thus more will be bond order, more will be bond order, shorter is the bond length. Shorter is the bond length, is the bond length. Okay. 5 point. Bond order also determines the magnetism in molecules. Bond orders also determines bond order also determines the magnetism in molecules. Determines the magnetism in molecules. Magnetism in molecules. Bond order is also determines the magnetism in molecules is that magnetic behavior. If all the electrons present in molecules orbitals are paired, then the molecules is dimagnetic. Okay. If all the electrons present in molecular orbitals are paired, then the molecule is dimagnetic. Then the molecule is diamagnetic. Okay. Diamagnetic. And if there are unpaired, electrons exist in molecular orbitals. The molecule is paramagnetic. The molecule is paramagnetic. The molecule is paramagnetic. The fractional value of bond order indicates the molecules will be paramagnetic. Okay. The fractional value of bond order indicates that molecule will be paramagnetic. Okay. Bond order and stability of some molecules are ions. Okay. Molecules are ions. Molecules are ions. Molecules are ions. Electron number Nb, Na, bond order and bond strength and bond energy. Okay. Bond energy. Okay. molecules are ions, electrons, numbers, and Nb, Na, and bond order, bond strength, bond energy. Okay. If H2 plus ion, H2 cation, H2 anion. Okay. Number of electrons 1. Number of electrons 1. And Nb 1. That means number of antibonding molecular orbitals. Okay. Okay. This is a Nb. That means number of electrons in bonding molecular orbitals. Number of electrons in bonding molecular orbitals. Bonding molecular orbitals. And this is number of electrons in anti-bonding molecular orbitals. Okay. That is 1. And anti-bonding, that is 1. That is 0. That is 0. And bond order 1 upon 2. And bond strength 1.06. And bond energy 64. Hydrogen molecules. Number of electrons 2. Number of electrons 2. Okay. Number of electrons 2. Number of electrons 2. Number of electrons 2. And number of electrons in bonding molecular orbitals 2. And number of electrons in anti-bonding molecular orbitals 0. And bond order is 1. And bond strength 0.74. And this is 103. Bond energy. Hydrogen, helium positive ion. Helium molecules positive ions. Number of electrons 3. Number of electrons 3. 2 is Nb and 1 is Na. 2 is Nb and 1 is Na. And bond order is 1/2. And this is 0.74. And this is 103. Next is helium atom. Helium molecule. Number of electrons 4. Nb is 2. And Na is 2. Bond order is 0. Bond order is 0. And bond strength is 0.74. And bond energy 103. Nitrogen. Number of electron 14. Number of electron 14. Nb is 10. And Na is 4. And bond order is 3. Energy 1.10. And bond energy 1.10. And bond energy is 225. Oxygen. Number of electrons 16. Number of Nb 10. Number of Na 6. And this is bond order is 2. And bond strength 1.21. And bond energy 118. Fluorine. Number of electron 18. Number of electron 18. And Nb is 10. Na is 8. And bond order is 1. And bond strength is 1.44. And bond energy is 36. Next is a molecular orbital diagram of some diatomic molecules or ions. Okay.